A few weeks ago, I had the opportunity to go visit XDev's labs here in Canada. I got to play with high-quality PPMs. We did some measurements on my Excitron 2000 calibrator, adjusted my HP3478. We also poked at a visiting 2602A with interesting issues, and I attempted a performance verification and adjustment on my own 2602 that I recently repaired, or so I thought. I had prepared scripts to automate the process, and the first steps were testing the voltage source mode, and that seemed to work fine. Then I went on to the current source sections, and I managed to kill the HP3458, well, the input fuse at least. And also, curiously enough, the firmware sort of froze. The firmware on the SMU front panel totally unresponsive. Nothing on the remote either. And I thought, well, long story short, it's some kind of hardware issue. Mind you, I had tested the scripts at home with my HP3458, but I think I was testing those scripts with channel B, which works fine. And also, I was probably not testing all of the ranges because I can't test the lowest current ranges, so that's why I had no idea there was still an issue when I showed up. Too bad this doesn't record smell. And I just powered on the machine with that connected, and I could smell death and smoke coming from that area. And I had hooked this up to multimeter here. Let's see if it still does anything. No, I think it's dead. Let's see what the damage is. So for the impatient viewers, here's the repair. I suspected it was a range-specific issue, so I focused on this area, the current sensing section, and it took a few minutes. I found a shorted MOSFET here. So these are dual MOSFETs in those SO8 packages, and I think it was Q72. So I replaced that, and then that was good. But I wasn't satisfied with just replacing a part. First of all, I wanted to know why that was causing the issue, and also I wanted to make sure there wasn't something causing that issue or another hidden and subtle failure elsewhere. Now, troubleshooting that was not going to be easy because I don't think we even have a block diagram. The best I could find was this. I mean, not super helpful. There's certainly no service manual that I know of, and even less schematics. I did look at the previous generation 2400 series with the assumption that they probably didn't redesign everything from scratch, and they do have a block diagram. I think I presented this, or I showed it a bit in my previous video, so that's kind of helpful, but not really where it matters here. The sense resistors, output stage. There's lots of ground symbols. There's O, G, and D. There's S. There's F. And I think there's another one. So anyway, there's no schematics again, but they do have a parts list. And that, combined with high-resolution PCB photos, thanks to Tin on XDevs for sharing these. So this, in combination with the parts list, you can sort of compare both and notice pretty quickly that the current sensing has nothing to do with the one in the 2600. I think these are high current sense resistors here, and there's some opto switches, and anyway, it's not really recognizable. So the only obvious course of action is to take a bunch of photos, stitch them together, and combine them like this, and then, so I did the top layer, I stole the bottom layer from XDevs again, and he also had some very nice X-ray photos, not of the whole board, but luckily the section that interested me. So I'd go in here and, play with, the usual tracing routine. Mind you, it's an 8-layer board, so the X-ray is absolutely a game changer, but it's not a cheat code. When you come in here and you try and follow a trace and it disappears underneath somewhere, and it was a massive pain. I'm not even going to say how much time I spent doing this. In the end, I didn't cover even large portion of this at all. I looked at this switching section here, some of the output here, the two relays. Those are the output enable relays. This is the output low. There's a guard sense amp here. That's the output stage, the power amplifier. What else is here? Some voltage regulators here, here, and there. Also these two, I don't know why they put them there. And what else I look at? Yeah, that's the main thing. I didn't even look at this. I know like this is the ADC here, so I wasn't really interested in that. This is voltage range switching, also not really interested in that. So that kept me plenty busy. I ended up with a few pages of dubious schematics with lots of incomplete and probably errors as well. And for the rest of the video, I'd like to explain, as well as I understand it, some sections of the circuit that I found interesting or mysterious. Just for some context, I'll start with the power rails. There's two independent sets of rails, giving 135 and plus 54. Those are relative to OGND. That's how they call it on the test points on the board. So there's that side, and there's the F side. Oops, there's also on this side there's a plus 18 and minus 18 as well. On the F side there's plus and minus 15, and there's plus and minus 5 as well. And it looks like this is connected to SGND as well. And my schematics are sort of using both interchangeably. So anyway, those are the two rails. Next, the power amplifier section looks like a push-pull audio amplifier, which is maybe more familiar, where you have a top side and a bottom side device like that, and they're both connected to out low, which is on the terminal block, and that's the L side. And that's this right here, so the output. And it has two parallel sections with output MOSFETs. And on this model that only goes up to plus or minus 40 volts, the output is much simpler than the 2400, which needs to stack a few more devices just because of the very high supply rails. So we don't have that. We do have more current. That's why there's two in parallel. And these rails, they're labeled 54 or 18. That's simply because of this around here. That's under software control to reduce dissipation if you're putting out lower voltages. Back to here, this IC, that's an LT1166. Power output stage automatic bias system. And that's supposed to sit as shown. It's not exactly the same circuit, but you recognize it's connected to current sense, like small value resistors between the source and the output, the common terminal here. And it does sensing, limiting, and some kind of other stuff, and I'm not sure exactly how it works. So that sits here. It's a bit odd to me because you're driving gates of two pretty hefty MOSFETs, and you're doing that by a 249k resistor. That's kind of weird. I'm most likely missing a connection or just misunderstanding the whole thing. Plus, when I probe this, I could see some, yeah, there you have it, 649 hertz PWM on pins 1 and 4. I don't understand that. I don't know why I'd be doing PWM on those gates, especially, anyway, if both channels were doing that. I don't think it's a fault. I'm not sure what the purpose of that is. And the pre-drive section doesn't really shed any light on it at all. It kind of looks like something you'd see in a more typical amplifier, but I'm also pretty sure I'm missing some connections, like this LED, which seems to be there for biasing current, but the voltage values I measured, like, they don't make sense. So take that with a huge grain of salt. And upstream for that is this op amp here with a test point 26 labeled E out, and that certainly looks like maybe the main error amplifier. So anyway, all that is on the low. Well, we're gonna call it low, even though it can go positive and negative, so it's mostly meaningless. Alright, so here's a different view. Those are the VO rails. It's missing plus and minus 18, but they're there. And current sensing lives between GNDO and the, well, that's on the terminal block there, H output. And the other set of rails here, the F rails, connected to SGND, and the main voltage reference is hooked up here to VREF, and that's around 6 volts, and it's rescaled to, it's about 4.1 to 4.2 volt, and that's the full scale value for the DACs and ADCs. And as it happens, the current sensing network puts out a value of up to 4 point something volts at full scale on each range. So that means between H and G and D O, you can have up to, well, it's going to be a bit more complicated than that, but you can have a few volts there. And the output section right here, is that going to work? Yeah, well, anyway, it's on that set of rails. So you can picture this moving up and down closer to either of those rails. And then the voltage between out low and, well, I erased that, but the H output here is how you vary the output voltage. Okay. And the last missing piece is, how does this set of rails, the F, G, and D, vary? Where is that attached? I'm not sure. I'm sorry, it's not clear exactly. So how does current sensing work? Well, how can you do that? You want to sense currents from 100 nanoamps all the way up to, well, let's call it 10 amps, right? Full scale. I think that's 9 decades of range. That's absurd. So obviously you can't just have one sense resistor. One obvious thing you can do is, well, let's put a big 0.1 ohm sense resistor, 4-wire sense for good measure, and then that'll be the high current ranges, and then we'll have progressively larger resistors and have some kind of switching arrangement here. That way, super easy. You measure the voltage on each side here, you switch the range as required, and boom. So if I go back 2 generations to the Keithley 236, which lucky for us we have schematics for, well, that's pretty much what they're doing here. A bunch of ranges here, some switches, and these also switches. So the concept is pretty simple. As usual, the devil is in the details. This is just one of the many pages, so I'm not going to go really in detail too much, but here are your sense resistors here, relays for the very, very low current ranges because they want to control leakage as much as possible. On the higher ranges, it doesn't matter quite as much, and they're using just a JFET here as a switch with some subtle things to drive them with a linear ramp. And the higher ranges are, yeah, here you go, a relay for 100 milliamp, and this massive JFETs for also ramps. The reason for the ramps is when you're changing ranges, they don't want an abrupt change, especially for the relays, I believe. So they sequence it so that, I think, bring the output current to 0, then do their linear ramp to switch over to the next range and then bring the output back. So anyway, lots of complexity there. I assume the 2400 is not any simpler than this. Although maybe a smaller parts count, I'm not sure. In any case, I was very sad to not recognize any of that on the 2600. Instead, here's what we have. There's that large sense resistor, 0.1 ohm again, that's for the higher current ranges. But then they put the other ranges in series like that, ending with a large 1G resistor. And that's the one labeled HMC here. The other resistors are this group of 3 I think they're 10 megohm each. Then there's this one here, the green one, 392K, and so on. Then there's a few hidden there underneath. And then the strategy is, well, okay, we want to bypass some of these. Like if you're running 10 amps, you're obviously going to want to have some sort of switch here to bypass this, and probably the next one as well. Whoa. Switch, please. Yeah, like that, and so on. Okay, so you need a bunch of switches. And then if you're, say you're measuring the voltage drop across this one here, well, you're going to leave the switch open, you're going to close all the other ones, and you're going to measure a voltage here and a voltage here, and subtract both, and was that the right symbol? I'm not sure. And that's going to be your feedback. Right, now let's see how they do it in more detail. So that's the chain of sense resistors, and you'll note on most of them they combine two ranges. So let's say for this one here, 40 ohm is used for 10 milli and 100 milliamps. So that's going to be a full scale voltage of 4 volts or 0.4 volts. And I assume there's a times 10 gain stage somewhere that I haven't found though. And here are some of the buffers, and those are CMOS input amplifiers. So they are very low input leakage, which is what you want. And they also drive some of the guard traces around here. So let me just give you a picture here. Those buffer amps are these on the bottom 8-pin devices, and they drive, so those are cutouts, and you see like this, the output of that amplifier drives this trace here, and this sort of little narrow island is driven from this side, and so on. So that's another way of controlling leakage all the way around that sort of big island. On this high current sense resistors, you'd expect the same thing, but no. There's absolutely nothing simple about this this SMU. So it's 4-wire sensing, and it's got this sort of diode connected transistors here. That's fine. But when I traced, it looked like there was a connection to SGND here on this pin. I don't get it. And then the output of that goes at least to, I call it V-shunt buffer, that drives the external guard signals, which you have access to. And I presume it also heads somewhere to the current sensing amps. And on the other side here, that's a bit more conventional. That's a buffer with a gain of, oops, I erased it here. It's a gain of 4. And it takes out the output from the negative input. So this will follow 1-to-1 the input here. And I believe that is the signal that's used for those guard rings on the PCB. It wouldn't help them if they used the times 4 signal, obviously. Just a quick tangent about diodes. So, beautiful, diode. What if you want a really low leakage diode? Well, you can use a transistor like they did here and use I think the base to collector junction is the lowest in leakage, so you can do that. You could also use a JFET. I probably got the arrow wrong, but anyway, the JFET diode is also very small geometry, very low leakage. But if you really hate people, then you look at your old application notes, and op-amp inputs provide ultra-low leakage clamps. Well, what do you know? Thanks to user Victorman who tipped me off to that. I hadn't thought of doing that, and it's I wouldn't say common trick, but it is like fairly well known. The idea is to use an op-amp that was optimized for very low leakage on the input pins and has built-in diodes, which, I mean, they make as small and as efficient as possible. So back to the schematics. This is what we have here, these 3, oops. And yeah, they're LMC7111, and the way they're wired is as a bidirectional diode. Well, it's the wrong symbol, but that's the main idea. You'll see why that's useful in a second. Here they used MOSFETs. I think they're not identified. When you beep them, they don't read as a bipolar transistor, so I actually don't know what these are. And here's how they're wired. Remember this buffer, and it has a 500 ohm, it's not a pull-up, but... So in most cases, the voltage on this side of the diode is held at the same voltage on the input. So you have the same voltage on each side, which means no current. Perfect. We'll need that in a couple minutes. These are when we're going to be deactivated each stage, that's where the current will flow. So those are very tiny diodes, but it doesn't matter if your full-scale current is 100 nanoamps or up to 1 milliamp. I think that's pretty much the most I'd want to be putting through those. And then that's why on the higher current stages, you have different combinations here. And the other one here that's still hidden. In fact, here it is now. What we have is 2 parallel MOSFETs. This one is inactive because it's tied gate and source. Have a little opto here. And then they enable these also parallel MOSFETs, and that's all a huge bypass. So that's used on high current ranges, 1 amp and higher. Oh, pretty easy, goes through there and all the way around. Okay, in the last bit I was putting this off. So you have this beautiful chain of MOSFETs, and those are your switches. And the way they chose to do this is not intuitive. Let's see. They tied all the N-channel gates together and all the P-channel gates together. They drive N-channels to minus 4 point something volts relative to GNDF or S. That voltage is gonna... Well, it's kind of at the same level as H, but not in any obvious way, of course. And by having a fixed voltage here of 4 point something, which you may recognize as something pretty awfully close to the full-scale voltage for DACs, that means that as the current through here increases, then at some point the voltage drop here reaches... let me see. It needs to overcome one body diode drop, so 0.6 volt across, let's say this one, plus VGS of at least 4 point something volts. And at that point, the MOSFET starts conducting, and then that means you're bypassing some of the current. Not all of it, there's still going to be a fraction going through. And as you keep pumping more and more current, then these stages automatically, well, that is, they get bypassed progressively. Let's see if I can illustrate this. I had to draw it because I thought I understood it, but it was sort of hard to believe until I saw it in action. So I have this set up. I have some current here. It's set up to do a log sweep from 1 nanoamp to 100 milliamps. I didn't draw a lot of things. I cheated a bit because the more I added things, the less it worked. So yeah, I forgot about all this stuff at the bottom. I have my gate voltages here fixed and a bunch of MOSFETs, and I have a trace here. So horizontal axis is current through the whole chain, or at least on the output. And let's look at diode current. Oops. Oh, this one, yeah. Oh yeah, there we go. I'm just going to plot all of these. I'm going to plot current. Should have done that first, actually. So this pink line, that's the current. And it's a straight line because my vertical axis is also logarithmic. And as you can hopefully see, let's look at the blue trace, diode 3. Like this level here, what do I have on my box here? That's picoamps, basically nothing. And at some point, it turns on, and then it starts conducting a large portion of the current. And then D5 takes over at some point, and so on. So those are the stages opening one after the other. And the green trace is OGND relative to the other ground here at the other end. So you can see, hopefully, that until OGND reaches 5.6 volts, like nothing happens. All the current's going through that 1G resistor, and then after that, the increase is not as fast because you're bypassing stages, and the only thing making voltage increase is that you're conducting through an extra set of body diodes and a bit of, well, I don't think RDS on really matters that much for those, but anyway. I know for sure there's more to it because, as I said, if I tried to simulate extra parts like this buffer hooked up to this side of the diode, then it didn't work really well anymore. And I think it also has to do with these connections that go to, let me see, to this multiplexer here, and yeah, it looks like it connects them to OGND. I don't know. Like I traced so that's a 4-to-1 mux with 2 channels, and I mapped the inputs, and they do sort of follow the ranges, but then you get duplicate states, and I don't know, it's just really weird, and I couldn't make sense of that. But still, I'm pretty sure that's how it works, and here's an example set of readings I took on the 10 microamp range at full scale. I was measuring voltages relative to SGND, which is kind of sort of the same level as this, more or less. OGND was at 4.95, that's here, and here I had 3.97, and actually initially I was measuring directly here with a DMM, but you're measuring a very, very high impedance node, and that didn't work, so instead I measured on the output of each buffer here. So 3.97 there, and then 3.96 here, and 41 millivolts here. And if you do the math, 3.96 minus that's 3.92 volts. Oh yeah, obviously, all the current was going through there, and most of it was getting shunted here. There was still a bit of a voltage drop here because nothing's perfect, so there was still a fraction of current going through there, but that's not important because the feedback loop's operating on these two. Oops, that would be, well, anyway, it's measuring that voltage here. Now for some bonus content, here's some other sections that I looked at. Here's this page. These are various regulators that I found. So let me start with this one. Now, this one is fed from plus and minus 54 volts, and there's those little 317s that I mentioned earlier, which are hidden around here. Those give plus and minus 27 right here, and then two Zener diodes here, and I'm guessing those are constant current diodes for various reasons, and I think Keithley either have shares in the manufacturer, or they really, really, really like them because they use them all over the place. And that gives plus and minus 8 volt rails, but it's not clear to me how, like, what the reference here, how it's centered. I found this connection, but that doesn't really make a whole lot of sense. They're kind of centered around OGND, but anyway. Interesting note, Q31 and 32 happen to be some recognizable parts. On this photo, that's prior to my replacement. They're these two here, and they were subject to a TO92 bodge. So that pretty much explains what their purpose is, and yeah, they're really cutting it short. You're dropping 19 volts across a little tiny SOT23, and you're feeding, I think, maybe a few op amps. It was a bit close. Then there's this set of rails here, and that would be these two D-packs there, and those are also from the plus minus 54 volt rails, and they're centered around out low, and they feed a bunch of op amps. That's pretty straightforward. And then this funky arrangement here, Q39 and 40. That is this one, and oh yeah, there we go, 39 and 46. This one's interesting. I'm not sure what to make of this. Then they have this sort of cross connection to the opposite rail, and the gate side goes to SGND, and my best guess is that that's sort of a sneaky way to have the voltage rails centered around SGND without pumping any current into it. That's my thought. And the reason to do that and not just tie it to OGND, because, you know, it's only 18 volts, is I think they want that centered and to follow SGND as it diverges from OGND, if you remember. This part here, SGND, which is sort of sitting around here. Then there's going to be up to, actually I measured up to 8 point something volts from here to SGND. And they clearly want some rails centered around here. So plus, what is that, 7 point something, and I forget. And they're going to feed a couple of these op amps here. Next, some meat and potatoes of output switching. This is a relay case 7. That's the one at the bottom of the board, and that switches two things. There's your guard trace and sense low. And your guard amplifiers here. Oh, they also really like the depletion MOSFETs. Here they're used as current limiters. Here too as well. And that is for local and remote switching. They have it opto isolated because the digital section is can be up to, I don't know, 50 something volts away. This is kind of weird. And that's just buffers probably going to voltage sensing circuits. The corresponding section on the high side is this relay here. So they have high and sense high. And they have this. And that's quite the mystery. I don't know what to make of this. Again, like very unsatisfactory, all this. They have these depletion MOSFETs again. But then, check this out. So, you have a unity gain buffer, just a 1-to-1 buffer, that's fine. Then look at this one here. So that's another crime with the same LMC7111 that they used as diodes earlier. But look at the rails, they have the negative up there, and that's I checked like 5 times. I know that's how it's wired, and they have those constant current diodes again, and that sort of felt like a diode, but I know for sure the pins 1 and 3 they go somewhere. I haven't found where. But I can tell on the X-ray and looking at it with a light, I can see these traces go somewhere. I never found where. So if it's a diode clamp, why, and what is this? Like a 500 ohm and 5K, so you have sort of a 10-to-1 ratio. It's really weird. And I remembered the ref manual says something about a contact checked functionality. And that's... Well, let's see if I can make sense of this. They run a tiny bit of current through the relay and your terminal block, I think. Or anyway, they're trying to make sure that the output relay and your contacts are reasonably low resistance. So it might have to do with that, but I couldn't really match any of this with the schematics, so, you know. Then there's also... yeah, I skimmed over this earlier. So these MOSFETs, if you recall, are for the high current ranges. So you're going to have the full 1, 3, or 10 amp range going through there. And this optocoupler, it's not a simple on-off switch. Well, first of all, they're using one with a photodiode output. But why would you want to vary the drive current? I don't get it. And the circuit that does this is not really... doesn't shed any light either. Yeah, this is the one. Just zoom in a bit. It does a few things. The easiest thing it does is over here. That's, let me see. That enables another set of MOSFETs. So that's just on-off switches here. Nothing really interesting. If I move up, 1A opto, yeah, anode and cathode. This is what's driving the optocoupler. I'm missing lots of ingredients, but what I see here is really not helping at all. Anyway, lots of unresolved mysteries. In any case, I'm pretty sure I fixed it. Fixed the issue I was having with Q72. Which one was that? Yeah, one of these died. One of these down here. I'm not sure why it died. One thing I suspected initially was I had a bunch of readings that I wrote down on a piece of paper, and one of them I circled, and it was showing 20.4 volts between gate and source. And actually, I think it was on one of these MOSFETs, not even the 72. And if you're familiar with MOSFETs, you'll know that 20 volt is a very, very common limitation. VGS max is almost always 20 volts. Yes, there are exceptions, but very rarely above that. And these IRF parts are no exception. Here it is. Yeah, there we go, 20 volts as well. And 20.4 was really not great. But I made a large number of measurements and I wasn't able to reproduce that, so maybe that's just a bad manipulation on my part. So in the end, I have no clue why this failed. I have no explanation. And also equally inexplicable is why would that have anything to do with the firmware freezing? Like why? The freeze happened when I was running 100 nanoamps. So this stage was probably conducting, and this had really nothing, didn't enter the picture at all. This should be off as well. So why? Anyway, I don't know. I have everything closed up. It works. I don't really intend to waste more hours to not understand. If anybody has secret information like schematics or block diagrams, let me know. Or if you know who worked on this and you're willing to blackmail them for me, I'd appreciate it too. All right, thanks for watching.